enjoying my videos. With another video, I'm back again. This video is very important, just like Newton's equation in classical mechanics. So far we have understand about the motion of wave, about the wave packets, its origin, and how the concept of wave packet is necessary, all these things. And now we can discuss about the motion of wave packet, and in the course of time we'll understand how the motion of wave packet can be understood in terms of single equation, namely the Schrödinger equation. So let's proceed to get the Schrödinger equation. So Schrödinger equation is nothing but just simply like the Newton's laws of motion in classical mechanics. As we noted in classical mechanics that the Newton equation provides us the position as a function of time, and then we find out velocity, momentum, energy, etc. And just like here also we have an equation like Schrödinger equation, we solve it and get a quantity known as wave function, and that wave function determines the state of the particle, which is explained by a wave packet. So Schrödinger equation is basically the analogous thing just like Newton equation in classical mechanics. So let's get that new Schrödinger equation. Let us always remember that Schrödinger equation cannot be derived. You have to arrive at it. This is simply itself a principle. So let's proceed to arrive at the Schrödinger equation. We'll first discuss the time-dependent case, and then we'll discuss about the time-independent case. Okay, fine. So let's go for this. What is time-dependent Schrödinger equation? So as we see that you just take the case of free particle case in order to understand time-dependent Schrödinger equation. A free particle means there is no potential incorporated in it, simply it has kinetic energy. So as you see here, the potential energy is 0, and in that case the total energy is simply kinetic. So basically the Schrödinger equation is dependent on two things. One is the quantization of energy, which is nothing but Planck's quantum hypothesis, E equal to h nu, and we get put this like this form, where h bar is equal to h by twice pi, and the omega is nothing but it is simply twice pi nu. So twice pi cancels, so ultimately h nu is equal to h cos omega, and this is nothing but p square by twice m is nothing is the kinetic energy of the particle, since it's a sphere particle. Again, the wave particle duality gives us that which is de Broglie equation, de Broglie relation, that the de Broglie relation is p equal to h by lambda, and if you put that since 1 by lambda is nothing but it's k by twice pi by k, so just introducing that definition for 1 by lambda in terms of wave vector k, that p is equal to h cos k. Remember that h cos is equal to h by twice pi, lambda is equal to twice pi by k, and then omega is equal to twice pi nu. So with all this we have two things, E equal to this and P equal to this, and first one is energy quantization and second one is simply de Broglie relation, and with these relations we can establish, you can arrive at the Schrödinger equation. Now since it's a wave, matter wave, so let's take the most general kind of thing, which is nothing but the plane wave solution, and that is nothing. A simple wave can be represented by small f rt. R is position and t is time, e to the exponential k dot r minus omega t, given by equation 3, and it's representing simply a plane wave, and it's a single wave which altogether make the wave packet as discussed in the earlier videos. So this is the single wave representation, and all the wave packet is represented by superposition of waves given by equation 3. Now since k is a continuous variable, we can instead of summation we can put that wave function that is representing the particle in terms of this superposition of waves in this way, where ak is a continuous variable and the limit is between k naught minus del k to k naught plus del k. We can this because of the continuity of continuity of the variable k, this equation 4 is represented in terms of integration. We can put it in, say if it's not a continuous variable, it will be like summation over all the states and e to the power k dot r dot minus omega t, or the summation of simply f rt, small f rt. And as ak is simply a heating factor, we can say it's a amplitude of the wave represented by equation 4. So using 1 and 2, we find that E is equal to this. Now differentiating equation 4 with respect to time, this we get like this, because it will affect only that exponential part, and exponential part, the time dependent part omega t, and this minus I omega will come out, and this is del psi by del t equal to given by equation 6. Similarly, then when partial differentiate this psi with respect to x, which will give us that this k dot r is nothing but it's actually kx dot x plus ky y plus kzz. If you take a dot product of this, and k is simply three components kx, ky, kz, and r is having three components x, y, z, and in that sense it's like this. So equation 7 representing the partial differentiation of psi with respect to x, and further differentiation will give us that I will again come out, this I and I will give it minus 1, and this kx will become kx square, and other terms will remain same. And remember that while differentiating with respect to x will affect only this term, e to the power k dot r. And we see that in the same way that differentiation of double differentiation of psi with respect to y will give us the equation 9, where we see that the part ky square is coming out, and for respect to z, kz square is coming given by equation 10. So all this differentiation has been done as given by equation 8, del square psi del x square, then del square psi del y square not given by 9, del square psi del z square given by equation 10. So and we also remember that ky, kx, ky all are simply the x, y, z components respectively, and the total vector is k square equal to kx square plus ky plus kz. So just adding up all these things, if we add all this partial differentiation, double differentiation, it will be nothing but the this minus nebula square psi. So minus nebula square psi is equal to this quantity, and adding up with the help of 8, 9, 10 we get this, because kx square plus ky square plus kz square equal to k square is given by equation 11. So we are left with equation 12, and some with a multiplication of the term h square by twice m, we get equation 13. That is h square k is bar square k square twice m ak and this quantity. So we are left with equation 13, which is representing the partial differentiation, double differentiation of psi respect to space, considering all the three components. So again, from equation 6, if you look back at equation 6, this is equation 6. Here is this term. We multiply this is bar. If you multiply this is bar, then I will give you minus 1, minus minus plus, and ultimately the equation 6 will become equation 14. So from equation 6 is multiplied with is bar, and that gives us equation 14. So on the right hand side is cos omega is here, and the integration part is here. So we are now left with 14, 13, and equation 5. Equation 5 was nothing, it was simply energy equal to cos omega. So this means that this equation 14, this part is cos omega is nothing, is E, and this part is 8 I cos by del psi del t. So and if you look at equation 13, we see that this is also simply energy term, this part, because energy is equal to h cos square k square by twice m, this representing momentum h cos k. So with this we are left with equation 15, minus h bar square twice m del square psi equal to I cos del psi by del t, and this is nothing but the time dependent Schrödinger equation for free particle. So we just arrive at the Schrödinger equation. Again repeat that you cannot derive it, we derive it with some kind of principles like energy quantization as given by equation 1, and then equation 2 wave particle duality, that is d-Boy relation, and consideration of plane wave solution for a single wave, the superposition of all these kind of waves, and with k being the continuous variable, and with some integrations and some partial differentiation, lead us to equation 15, which is nothing the time dependent Schrödinger equation for a free particle. So we are thus left with these equations, and this equation simply showing you that we are now at a position to say that Schrödinger equation has been in front of us. So it's a simple case where we took free particle case. Let's now take the particle in the field case. In that case, that field will not be equal to 0, and potential has some non-zero value. So with this, equation 5 will now become this. In the earlier version, only this term was present, because this term is nothing, it's the kinetic energy term. So since now potential is present here, so total energy is equal to h cos omega is equal to h cos square k square by twice m plus v RT. V is simply the potential. Now we just, since psi RT is already given, we multiply this with VRT and we get equation 17. So only difference that we get here is that this term is coming here. So next, adding 13 and 17, we get this 17 here, and this is 13 here. Left hand side is this one 13, and left hand side is this one. So it's lead to like this: minus h bar square by twice m del square psi plus VRT equal to this. So within integration, this term will come because already is there, and now since it is VRT, this is given by equation 17 now, we'll also include it here, and we'll be left with equation 18 now. So using equation 14, 16 and 18 now, which are like this is equation 14. If you look at this equation 14, it's nothing but it's simply the partial differentiation of psi respect to t, and this term is energy. And then 16, if you look at this equation, this h cos omega is E, so we'll represent this by E, and this is E, and similarly this is E. So left hand side, or the equation in 14, the left hand side is simply equal to the right hand side of equation 18. So ultimately we're left with this equation 19. So minus h cos square twice m del square psi plus v RT psi RT equal to I bar del psi del t is 19 is time dependent Schrödinger equation for a particle in a field. So we are just getting time dependent Schrödinger equation for two cases: for a free particle given by equation 15, and for a particle in a field given by equation 19. So Schrödinger equation is nothing but simply it's a basic equation giving us the representation of motion of wave packets, and thus we can see that the wave packet motion can be discussed in terms of single equations whose solution would give us the wave function, and in terms of wave function we can explain many of the phenomena related with quantum mechanics. So these are some assessment for you. What is Schrödinger equation? What is its significance? What do you mean by the dependence of Schrödinger equation, time dependence? What are the basic equations to arrive at the Schrödinger equation, and then arrive at the Schrödinger equation? Just simply how we proceed to get the Schrödinger equation. So all these things are included in the video, and I hope that with this video you can understand how Schrödinger equation evolved out, how Schrödinger equation are based on, and then how it can be arrived at, and all these mathematical things that we can discuss here. So thank you very much for watching. Keep watching, and don't forget to comment on the videos and put suggestions. Thank you very much once more.